All right, we're going to start off with a few review problems from our previous lesson on exponential growth and decay. And then we are going to look at a couple of special examples of exponential growth, especially here in just a minute. But I'll also show you how it ties to decay as well. So the first thing, a little bit of review, using the calculator to find the equation for this table. Notice your x values are across the top, y values across the bottom. And I'm going to go to my Desmos calculator, and then I'm going to hit the plus sign, go down to table, and I'm going to type in -3, -2, -1, 0, 1, and 2. And so then I'm going to go to my y values, and we'll start with 50. And we'll go to 25, then 12.5, and then 6.25. And then we've got 3.13 and 1.56. 3.13 and 1.56. Now if we look over here on our graph, we should be able to see that this particular function is a exponential decay function. It's kind of hard when you stretch it out a little bit, but hopefully you can see that these guys right here are dropping down very rapidly, but then slowing down. And so what's going to eventually happen is it's going to level off right here. So to find my equation, I go y1, and then I use my little approximation type symbol, the little squiggly. A times b raised to the x power. So I'm going to click on the little keyboard and raise it to the power of x1. And it's going to tell me what my b value is, about 0.500, and that should make sense. They're basically cutting in half every time. And 6.25 is my a. So my equation would be y equals 6.25 times the 0.5 raised to the x power. And pay attention here. Notice what's happening. Again, it's cutting in half every time. That's why this is cutting down in half every time. But notice my beginning amount is 6.25. The reason that is not 50 is because 6.25 is where the actual graph crosses the y-intercept, the y-axis. So that's why that is our beginning amount. It's always important to understand that when it comes to the graphs of these. All right, do a little bit more review. Question on these is, are they growth or are they decay? And if you can, I want you to think about what would be the percentage of growth or decay. So I want you to think about that. I want you to pause the video and try it out and see. The two at the bottom are a little tricky. All right, so hopefully you tried it. Hopefully you looked at these. This is going to be growth. The reason I know that primarily is because this inside the parentheses is bigger than 1. It's 1 plus the rate. And to get 2 right here, the R would have to be 1, which is 100% growth. The next one is decay. The reason I know this one is decay is because this is 1/2. This is less than 1. It's 1 minus R. So that means that the R would have to be 1/2 or 0.5, because to get 1/2, I'd have to do 1 minus 0.5. So that would mean it would be a 50% decay, very similar to the one we did just a few minutes ago on the calculator. The final one here is 5/6. That is also less than 1, so that has to be 1 minus R, so this would be decay as well. The tricky part on this one is realizing that to get 5/6 here, you would have to do 1 minus 1/6 to get 5/6, which is approximately 16%, 0.16. Not perfect, or 17% if you get a little bit, round that to the hundredths place there. So that would be approximately 17% decay. Now the two at the bottom I told you are kind of tricky. This negative exponent, you have to remember what a negative exponent does. It's going to take this right here, the 2, and it's going to flip it every single time. Remember we talked about how the negative exponent moves it to the opposite part of a fraction and makes it positive? Same thing over here. It would take the 1/2 and it would move it because it would take the 2 and move it up to the top. Anytime you have a negative power, it basically moves the thing that is raised to a negative power to the top or to the bottom. So actually this one right here, we're not going to worry about the percent on this one. This one would actually be decay and this one would be growth. So these are a little tricky. These are the ones I want you to be aware of. Anytime you raise it to a negative power, even though this right here is bigger than 1, we would expect it to be growth. The negative exponent flips it down to the bottom of the fraction, so it actually makes it decay. Same thing with this one. The 1/2 makes me think that it's decay, but the negative exponent flips it and makes it move up to the top to make it growth, actually. So these two guys right here are a little weird. So I wanted to show you those. You don't see them a lot, but I wanted to show you those so you can be aware of that possibility happening. All right, so let's move into another little example of graphing. We haven't done a graphing problem in a few days here. So let's look at this graphing problem right here, 3 to the x minus 1 plus 2. Now I'm going to come back to this best fitting equation here in just a second as well. We're going to do that one as well. I am going to primarily sketch this little graph here. So let me cover that up so nobody's distracted by that. So I am primarily going to sketch this graph. My reasoning behind that is I'm going to sketch this graph because I don't want to go through and try to draw out a big detailed graph, because you're not going to have to draw extremely detailed graphs for these when it comes to the quiz and test. So what I want to do though is I want to remember what the -1 and the +2 are actually doing. The -1 and the +2, remember we talked about it, is that whole opposite same technique where it's moving it left and right and it's moving it up and down. So really all I need to do for a table of values to get a few points is I'm just going to do the 3 to the x. I'm not going to do the whole thing. I'm just going to do the 3 to the x because that's going to make my table of values very easy, or much easier than trying to do the whole thing with the -1 and the +2. My reason for telling you that is because it'd be hard and tough to type in the calculator with all the crap there. So I'm going to take 3 and raise it to the -2nd power. So I just take out my handy dandy calculator, and I'm not going to do this every single time. Actually, I'm going to go to the TI calculator a little bit here. So I'm going to take it and I'm going to get out of there. 3 raised to the -2nd power is 0.11. So basically a nice little decimal here. 3 to the -1st would end up being 0.33. 3 to the 0 would be 1. 3 to the 1st would be 3. Remember our y-intercept right here, 0, 1, is because there's nothing out in front of the 3. There's no base number in front of the base 3. Then 3 squared would be 9. So now if I graph those points right there, those points right there would be this graph, the 3 to the x. So I'm just going to kind of sketch where that would be. Basically, you're going to have, like we talked about here, your values for x and y. Essentially what you're going to have is you're going to have a graph that's really close to the axis, a little bit above that, goes through 0, 1, my beginning amount there, 1, 3, and then 2, 9 way up there. So that would be the graph 3 to the x power. Remember we talked about how that would give me an asymptote, is the special name for this right here, across the axis. But because this has this -1 and this +2, I just want to take this graph now and I want to move it. And so I'm going to move that graph right 1, because it's the opposite, up 2. So I'm going to go right 1, up 1, 2. Right 1, up 1, 2. Right 1, up 1, 2. Right 1, and then up 1, 2. So it's basically going to be right about here. So I've moved my whole graph right 1 and up 2. Notice that right across the graph, again, now because this graph moved up, there is going to be now an asymptote, like we said, up 2 spaces, because this graph will never come down below this asymptote here. So please make sure that you understand that concept of that asymptote being there. If you need to, it'd probably be a good idea to erase the red graph to get it out of the way so you guys don't get confused and think the final answer is the red graph, because it's not. And I'm probably going to have trouble just because I put too much junk in the way here. But we'll do as best we can, erasing the red graph. There we go. That's the closest we're going to get. So I won't worry about erasing that point. So here you have your graph. You use these points because they're easier and quicker to find in the calculator, and then you move them right 1 and up 2, right 1 and up 2 the whole time. If you do that, you'll get your graph. Okay. Notice the domain is all real numbers because it touches every x value. It keeps going this way forever, keeps going this way forever. But the range is anything above 2. It will not go down here, so the graph doesn't touch down here. All right, so the next thing I want to do is I want to do one more example using our calculator, and then we'll get into a couple of special exponential growth problems, specifically if you other types of bank accounts and a growth. So it says find the best fitting equation. You have these values for x, -5, -4, -3, -2, -1, 0, 1, and 2. And so we're going to take those and we're going to go to our table again, typing those in. And I'm sure there's probably a real pretty way to do this, but just because of the sake of time, I'm going to just type right over the top of these. Yeah, there we go. Oh, now it's not going to like me, of course. There we go. -5, -1, -4, excuse me, -3, -2, -1, 0, 1, and 2. And then we're going to go 13, 5, 0. So we'll start here. 13, 5, 0. -4, I believe, was the next one. And then we're going to go -6, -6, 0, 7. -6, -6, 0, 7. Now I am going to delete this equation that we did earlier because I want you to see something. So if you look at those points right there, do those points look like the ramp shape that we're used to with a exponential function? It's going like this, and then it's going back up like this. Hopefully you're screaming at the computer, no, that does not make the same shape that we've been used to, of that little ramp shape like we're talking about. So this actually goes back to something we've done in the past. If you look, this would be a parabola. It goes down and then it comes back up. So when I go to my equation here, when I type in y1 in my little approximation symbol here, I'm not going to do a times b to the x. I'm going to go back to my old quadratic days and do ax1, and then I'm going to square it, plus bx1 plus c, ax squared plus bx plus c. And then the calculator still does all the work for me, and it tells me what my actual a and b and c are in the problem. So then I can take those and I can approximate where my graph ends up here for this parabola. The parabola, obviously, if you look over here, doesn't fit perfectly, but it does give me my a and b and c. And so this equation actually is y equals 1.26x squared, 2.77 x, and then I believe the last one was minus 4.23. So minus 4.23. So be careful. Anytime I give you one of these tables, it doesn't mean it's automatically going to be an exponential function. You still have to remember all the other functions. Now, there is a way to do this by going to the Stat menu and going to Edit on the old calculators. If you have one of those at home, you can enter in your points, and you can find the regression by going back to the Stat menu and going over to Calculate and going down to the type of regression that it is: linear regression, quadratic regression, cubic, quartic, and then you get down here, there's even down at number 0 there, exponential regression. I'm not going to go through those because I feel that the Desmos calculator is probably the one that most of us have the access to at home anyways. So it's going to be the one that you can use the most, but it still would give you the same type of equation if you did that with this one. So if you do have a question on that and you want to know how to do that, I can definitely take you through that. We'll just sign up and do a WebEx meeting sometime and I'll show you how to do it. All right. So a couple of special things I want to talk about. One of those is half-life. You may want to go through and copy down some of the stuff that I'm about to show you right here with half-life. Half-life is sometimes you are talking about things in science or in the medical field especially. Things decay at a certain rate and they have what is called a half-life. In other words, it is a amount of time that it takes for a substance or some material to decay completely in half, to cut in half. Specifically in the medical field, we're talking about a lot of times like cancer treatment, the radioactive substances that they use in those cancer treatments like chemo are going to decay at a certain half-life, meaning half of it will disappear after a certain amount of time. What I want to point out is that anytime you see a problem that deals with half-life, you always have that same characteristic, a times b to the x, but there's something that you need to watch out for. In half-life, you always are going to have to take whatever time you're plugging in and divide it by what the actual half-life is. Now, let me show you what I mean by that in just a second, okay? But the other thing to notice is that the b value right here in the middle will always be 0.5 because you're talking about how long it takes for something to cut in half. So there's an example up here. It says a hospital prepares a 100 milligram supply of technetium 99M. Again, this is a radiation type treatment, which has a half-life of 6 hours. So every 6 hours, this guy's going to cut into half. Now that means you could go through and you could actually use your calculator to help you a little bit here. You're taking 100 when you first make it, that's at 0 hours. 6 hours later, there's 50. 12 hours later, there would be 25. It's cutting in half every single time. So you could use that to use your calculator to help you as well. But again, I've also given you a nice little setup here. If you'll pay attention to this little setup right here, it's always going to be the beginning amount, which in this case is 100. It's always going to be 0.5 when you're talking about half-life. And you just take the x divided by the half-life, which is 6 hours. So this is your little formula to figure out how much substance you have left over. So then we could take this little formula right here and we could figure out, okay, after 12 hours, how much is left? We plug in 12 right here. It's going to be 12 divided by 6, which is 2. And then it's going to be 100 times 0.5 raised to the 2 power. It would end up giving me 25. But then what I could do is find later on, notice this one's 75 hours is not a nice, pretty divisible number by 6. But it doesn't matter because then I can use the calculator to do 100 as my beginning amount times 0.5 raised to the 75 over 6 power. So I can still use my little formula to figure out how much is left after 74 hours, and it would be 0.017. I would probably say 3 decimal places would be a good idea on this one because we're talking about something pretty serious in the medical field, but it'd be 0.017 milligrams should be left. So that's how you approach any half-life problem. Basically, again, you have the beginning amount like we did before. It's always going to be 0.5 because we're always talking about it decreasing or decaying by half with a half-life. And then you divide the time that you plug in by the half-life. One little caveat here is that you have to watch out. It has to be hours here. You have to have your half-life in hours. Sometimes it's in years. For instance, I'll give you an example, and this is one of the reasons that You'll hear Mr. Harrison argue when it comes to some of the age dates that are listed in some of the science textbooks. Carbon-14 is another thing that they use half-life for. And the half-life of carbon-14, and I'm going by memory here, I'm pretty sure is 5,730 years. That means whatever amount you have times 0.5 raised to the x over 5,730, that would tell you how much amount is left. Here's the issue. When you get into such low untraceable amounts here, there's no way possible for you to actually get a very, very good answer for how old that item is. Not to mention that it has its upper limitations. There would be a limitation of, I think, carbon-14 dating has an upper limitation about 60,000 years, meaning if you see carbon-14 in something, that means it's less than 60,000 years old. I think some textbooks will say it's 100,000. Even then, that means if you find carbon-14 in any fossil or in any rock, that means it has been there and it was made less than 100,000 years ago. Guess what? They find it in dinosaur fossils. Let that sink in for a second. That means it has to be less than that upper limit that we've talked about. So that's the general idea behind half-life. All right, so I've got a couple more special examples. Those deal with compounding interest. We talked about compounding interest in the other video, but we didn't get quite as much detail as real life actually entails. Typically with interest, you also have different times, or different number of times, I should say, that the interest is added each year. Some savings account add that interest monthly. Some savings account do it yearly. Some savings accounts will do a daily check on the balance. But those are a little bit rarer, and usually the percentage interest is very low if that's going to happen. But in the negative side of things, on the bad side or downside of things, credit cards also do this. Credit cards are notorious for adding interest, which means the interest you have to actually pay to borrow the money. They actually add the interest to your account monthly or daily, and so it can be a very bad thing. So I want to show you what that formula looks like. It's slightly different from the other formula, but it means basically the same thing. Instead of y equals, they'll put a equals. Instead of the beginning amount being c, they'll put p for principal. And then 1 plus r over n raised to the nt power. And I know that looks like a whole big jumble of mess, but make sure you notice a couple of things. Number one, the rate is still the same, still the percentage rate. The beginning amount still the same out here. The t is still the time. The only thing that really has changed from the other formula that we did is right here you have the n is the number of times interest is added. Essentially what's happening, I'm going to try to explain this, and it's hard to do a little bit without me actually looking at you face to face, but what's happening is they take that R, that percentage rate, and they divide it up over the number of months, or they divide it up over the number of days, or they divide it up over the number of, if it's quarterly, 4 times in a year, they divide the rate up to how many times you add the rate. Then they multiply the time by how many times you add the rate. So essentially this n is helping and sort of hurting you at the same time. They're taking that percentage rate, which is the APR, annual percentage rate, and they're dividing it up over the year, how many times you add it. But then they're also giving you multiple times a year. So that's why it multiplies by the time. So what it looks like, if you look down at the example at the bottom down here, you have deposit of $1,000 into an account that pays 8% interest. Find the balance after 1 year. So we're going to figure out what the balance is after 1 year. Notice the first one is annually. Annually means you take that beginning amount, 1,000. It would be 1 plus the rate, 0.08, divided by 1, because 1 time annually. But that's just going to be 0.08. Guys, if it's annually, it's just the old formula that we're used to. And then you raise it to the time of 1. If you take out your calculator and type that in, you're going to notice that if you take it out, type in 1,000, and I'm going to use the Desmos calculator here, 1.08, and you raise it to the first power, $1,080. Because that is just one time a year that uses the regular old formula. But when you get to one like part B and it says quarterly, you are adding that interest how many times a year? That's right, 4 times a year. So they divide the 0.08 4 times, and they multiply 4 times 1, because you're not just adding it one time in the year, you're adding it 4 times. So you divide the rate and you multiply the time. So again, though, now the formula is just typing it in the calculator, though. This does not change the fact that the calculator essentially is doing all the work for me still. So I take this and I do 1 plus 0.08 divided by 4. Let's see, it's not going to like me. There it is. And then I raise it to the 4 times 1 power. I'm going to hit my little time symbol there. Oh, no, it's not going to like me. Why do we not like that? Let's try it again. Let's try this. Yeah, there we go. So 4 times 1, we're going to multiply that in the parentheses. And so that's going to help my calculator's now going to know what to do there. So notice it's a little easier on the TI calculator when you raise it to a power and you can actually type in the 4 times 1 in the actual exponent up here. It's a little bit easier than Desmos is, but still works the same way. I'm going to have to use parentheses on Desmos. So notice it gives me a little bit more money, $1,082.43. So $1,082.43. Not a lot more, but yeah, hey, again, quarterly is going to be a lot more. Not a lot more, but it's going to be more, than annually. The biggest issue, though, is the fact that this hurts you when it comes to something like a credit card. You're going to have to watch out there, because that means if they're adding interest monthly or daily, they're absolutely crushing you with interest fees, especially if you don't pay those minimum payments. Or if you only pay the minimum payments, it can still hurt pretty bad. And you end up paying, if you bought a $1,000 TV on your credit card and you pay only the minimum payments, it'll take you 10 years to pay it off, and you'll end up paying almost $3,000 for it. That's the problem. You got to watch out for how compound interest works. All right, so the next one here says daily. So same concept. We're going to take 1,000, 1 plus 0.08 divided by 365 days in a year, and multiply the 365 times the time of 1. So then I take out my handy dandy calculator, do 1,000, 1 plus 0.08 divided by 365, close my parentheses, raise it to a power here of 365 times 1. I don't know why I keep accidentally hitting the letters there. $1,083.28. $1,083.28. Now again, I know this doesn't look like a whole lot of difference, but remember, we are talking about $1,000 on 8% interest for 1 year. We're not talking about multiple years. Multiple years will be even uglier, because then you'll start having a bigger number up here for the exponent. And what I mean by uglier, I mean in the case of the negative side of things, like a credit card. For the bank accounts, this would be awesome. Typically, it's not going to happen where the bank account, they're not going to give you that much interest. Normal bank account, that is. The last one on here is continuously. Now, I know continuously looks crazy. You're thinking, what do you mean, adding interest all the time? Yeah, technically that's what that means, but it is a different formula. Now, to get the formula for continuously, usually I go through in class a little bit more detail of how it happens, but I'm not going to do that, kind of simplify it here for you. I will show you that what it comes from is if you have 1 plus 1 over n raised to the n power, if you start plugging in numbers into this right here that get bigger and bigger and bigger and bigger and bigger and bigger, essentially what I'm saying there, as you plug in numbers that are closer to daily or maybe hourly or every single minute of the year, that number is going to get bigger and bigger for the n value. If that number gets bigger, it gets closer and closer to this special number called the Euler number. Not Euler, the Euler number. It is the special number E. The cool thing is that little E is on the calculators. It's approximately 2.71828182845.9. You don't have to know that because that little number is going to be on the calculator. Basically what it means is this. Anytime you have continuously compounding, you use what we call the PERT formula. And yes, if you look at it, hopefully you'll be able to tell the reason the name is PERT formula is because of what it spells. But basically, you take the beginning amount. So I'm going to use the light blue color here. You do 1,000 for my beginning amount times this little special number E raised to the R times T, or 0.08 times the time power. Now, guys, essentially what's happening here is what this is doing is showing what would happen if you're adding that 8% continuously. The 8% would be divided out over the year, but it'd also be multiplied by the year, but it would give you this continuous amount of interest that's added. No, a bank account is not going to do that for you. But there are things in real life that follow this continuous formula. And so you'll see this little E raised to the RT, or even really the beginning amount out in front of it, E raised to the RT. You'll see that in a lot of different formulas, especially in a science context. Let me give you one example too that you'll see. You'll see E raised to the negative RT. Remember we talked about that a little while ago, that negative RT is going to flip this. So instead of growth, it would be a decay function. There are a lot of things in real life that decay at a constant rate, continuously. It's kind of a nasty example, but I'll give you an example. This would be when a person is killed, a dead body decays to a temperature that is a constant temperature of the surroundings. So there is a little formula called Newton's law of cooling that describes how that body could cool down to that temperature of the surrounding area around it. And scientists and forensic investigators actually can use this type of formula to figure out how long the body's actually been there. Yes, I know that's kind of a weird example, but you can also look at it. It's the same kind of example of if you take a boiling hot soup off the stove, it'll eventually cool down continuously to the temperature of the room. So essentially, though, all you have to be able to do is type in the calculator again, because you've got this 1,000, you've got this little base E. This base E is basically a special number, kind of like pi. So it really is the number 2.71828182845.9. It actually keeps going forever, but then you just have to type it in. All right, guys, sorry about the little glitch in the video there. So we just type in 1,000 times the E. Notice there's where the 2,718, it's already multiplying it by the E. But then I want to raise that E to the RT power. So I'm going to use my little parentheses again, 0.08 times the time of 1. Again, R times T. So then it tells me $1,083.29. Notice that there is not a lot of difference between daily and continuously when you talk about only 1 year of interest and only $1,000, and the fact that 8% interest, that's not extremely high when it comes to things. It is high for a bank account, but so you're not going to see a ton of difference here between daily and continuously, because daily is adding the interest every single day. So that's why, again, you kind of go back to that example of the credit card. They charge really high amounts of interest, and they charge sometimes daily interest or monthly. They're really ripping you off when they give you that much interest and they compound it that many times. So these examples that I've gone through today with you are just some extra examples of specific types of interest and exponential growth and decay. If you have any questions, please don't hesitate to notify me, and we can set up a WebEx. I may try to get on WebEx sometime today and tomorrow, so I can go through and give you some extra help. So, love you guys.